Hello, colleagues and Dr. Marvin. This is week 3, deep learning concept seeding and discussions. My topic for discussion is reinforced deformable neural networks. I'm Patrick Anako, the presenter. I'll be taking you through a background to the topic. I'll cover reinforcement learning at an introductory level. I'll also look at the topic in brief itself, that's reinforced deformable neural network. We'll look at some key concepts there. Then we'll look at reinforcement learning algorithms, the number of algorithms involved in this concept. Then we'll look at an experimental exploration of all the concepts. It's going to be a simulation. Then we'll discuss the results. So to begin with, we'll just go through some key concepts and terminologies when we talk about reinforcement learning. So first, let me just give a brief definition of what reinforcement learning is in relation to deep learning or machine learning. Basically, reinforcement learning is a technique that allows a model or an agent to maximize a particular outcome in any given situation. So if we are to compare it with, say, supervised learning, whereby the model learns based on pre-trained data set. For reinforcement learning, the model learns from experience, okay, and mostly an uncertain input. So the key things I want to cover in this part is, one, an agent. We need to define what an agent is in this concept. So in relation to reinforcement learning, an agent is usually an entity that uses a policy to take certain actions. Okay, and let's also see what an environment is. In this context, an environment in this context could be our deep learning model or a neural network. Maybe another analogy would be, to make this make more sense, would be if you look at a robot. A robot would be an agent. A robot takes action based on the environment it's in. Yeah, so that's another close analogy. Then also we have terms like state and reward. The state is usually the situation that the agent finds itself in. Okay, there are going to be multiple states as the agent learns, and as the model improves, the state is going to change. Then there's also an action. So an action is a result of the agent taking a decision that then results in an action. Then we have policies. Policies are what allows the agent to make those decisions that lead into certain actions that have to be taken by the agent. Then we have RL, that's reinforcement optimization problem. Because this is continuous learning, there is usually a lot of optimization involved to guide the model into learning, effectively. So in our typical case, the policy will be our neural network. In this case, of course, it's all part of the environment. The policy is going to work within the environment to influence the agent into taking certain decisions that result into a given action. Uh, the reinforcement learning follows the Markov decision process. It's a probabilistic concept where there are a set of possible environment states, then there are a set of models, there are a set of possible actions that can result from a given policy, or yeah, then there are rewards. Okay, rewards are a result of certain actions or decisions that eventually result into actions. Then we talked about a policy. A policy now it's more like the entire solution to the problem. You solve the problem by defining those policies. So if you look at a mathematical expression of how this would work, the probability of the next state, because the state of the agent determines the action it's going to take. So the state of the agent at any given time is derived from the next state's probability, okay, considering all the previous states. So here is basically a simple mathematical illustration of how the state of the agent is determined. Then let's look at the next concept of deformable neural network. This basically extends the convolutional neural network by introducing deformable convolution and deformable that's region of interest polling. This is here's an illustration of how the convolutions work. It's basically how the sampling is done in two cases. Case one is for the convolutional neural network, which has fixed receptive fields. Those are the fixed kernels. So when we are doing sampling using convolutional neural networks with fixed receptive fields, you find that the kernel structure, if it's a 3 by 3, if it's a 5 by 5, it's going to be used throughout the convolution. So regardless of which iteration you're doing, which sample you're taking, if you take 10 samples, the structure is going to be the same. So they introduce some bit of inefficiency in how the features are going to be extracted. So to overcome that, there is the concept of deformable convolutional neural network. This basically has adaptive receptive fields. So instead of the fixed kernel, the kernels use deformed convolutions, which are just based on offsets to shift the sampling points. So diagram below, that's diagram B. You see how the fields are adapted to the input shape or the object. So this sort of improves how the features are going to be extracted. It's going to capture more features as the sampling is done. Furthermore, if we are supposed to look at this picture and ask ourselves which technique of the two we have just discussed can give us better effectiveness when we are doing sampling and feature extraction using convolutions. So the image A, if you look at the image A, the above row, that's row 1, say there are two rows here. So row 1 is using the fixed receptive fields or fixed kernels, and the below row, that's row 2, is using the adaptive receptive fields, in other words deformed convolutions. So you can see that we have better chances of capturing more features while we are sampling across the dataset or a given image. So obviously deformable convolutional neural networks improve a model's ability to adapt to inputs with varying geometric orientation. So regardless of the shape of the input image, deformed convolutions outperform the previous technique. So here we are going to introduce reinforced deformable neural networks, which basically combines reinforcement learning and deformed neural networks. It dynamically adjusts the receptive field of the convolutional layers for better feature extraction. This is just a continuation of the idea in the previous slide. The key concepts here: reinforcement learning agents to observe the current feature map. Okay, we looked at an illustration earlier. So the reinforcement learning agent observes the current feature map, then it adjusts the kernel positions based on a reward, e.g. accuracy of detected objects. If the actual accuracy is higher, it's going to adjust the kernel position to improve the accuracy further. If the accuracy is low, it's going to equally do the same to try and improve the accuracy of, improve the kernel positions to obtain better accuracy. Then the model further optimizes its receptive field dynamically over multiple training steps. So if you're training on a given data set, let's say you have an image data set of 10 classes. If you do a training sweep, one sweep across all the 10 classes for all the images, then you do another sweep, then a third sweep. As you keep doing that, the model dynamically adjusts or optimizes the receptive field in order to try and learn more and more about the data set to make better prediction if you're doing prediction, or classification if you're doing classification, and so on. That's the idea I wanted to pass on. Then look at some reinforcement learning algorithm. There are basically two categories from my research I carried out. There are those that are policy based, which basically learns a policy. Typical example here is the reinforce. Then there is model free methods, whereby the agents learn without a model, without knowing a model of the environment. So in this work I looked at reinforce, which is an acronym for reward increment equals to non-negative factor times offset reinforcement times the characteristic eligibility. I've given a link here for you to have another deeper look, if you wish to, at some of the other types of algorithm that we may not talk about here. So we are going to look at some key features and aspects of reinforce. Like I mentioned, it's a policy, but it uses gradient algorithm, and it trains agents to make sequential decisions in an environment. So usually one decision leads to the other decision in a sequential manner. That way the agent is able to learn from the previous knowledge. Then it encourages high reward actions and discourages low reward action. So if a reward is, for example, 1, actions that come from the reward 1 are going to be more encouraged. If the reward, say, is -1, then such actions are going to be discouraged. In other words, the model is not going to learn from such actions. It's going to discourage or ignore such actions. Then it updates neural network parameters based on the obtained rewards. So as it learns, the model parameters are going to be adjusted. More knowledge is going to be added, or it's not going to learn anything based on those rewards. Let's look at the experimental setup. What I've done here is to come up with a training a policy gradient agent for image classification. Basically, we are training a reinforce agent to do image classification. So 3 key aspects I looked at. One is the policy gradient learning, whereby the agent updates its policy directly based on the reward. We shall see these in the simulation. Then there is mini batch training, which offers efficient processing of data in small batches. So instead of doing our training on one image, for example, at a time, we do it in batches. So we introduce some efficiency in the training process. Then there is performance monitoring, which tracks rewards per epoch to evaluate the learning process. What I mean here is basically, as we are doing this training, we are going to log the rewards that come out of each evaluation of an iteration. If, for example, we do the first strip or first training iteration on the entire data set, we capture all the rewards for that phase, we store it, we do another training on the same data set, another iteration going through all the processes, so we keep a record of all those. Then at the end of it, we do a plot to see whether the model learned or it didn't learn anything from the data set. And the tool I used is PyTorch, which we use mostly for tensor operations and in model training. There's a setup for the experiment. This is a purely Python code and structured. The image on the left shows the structure of the code. We have a file structure, this dataset directory, but the key thing I want to focus on here is the agent, reinforcement learning agent, reinforce agent.py. We are going to look at that script, some code base from that script, to understand the concept we discussed earlier. So here is a high level flow of the program. It involves loading dataset. So there are some scripts that load for us the dataset from the dataset directory. Then there is another part where we reinitialize the agent, that's the reinforce agent. Then the core part is the training loop. It's a loop because it's going to do multiple trainings on the dataset in a loop. As the model learns. So you can see there is fetching the batch from the data loader. Once we load the images, we create batches. So the batch is going to be fetched one after the other. There is a check to identify the device on which the application or program is running. If it's going to be running on a local PC, it's going to detect, then switch to CPU. If it's going to run on a platform, for example, Colab, it's also going to detect that and switch accordingly. So this test was done locally on my PC, so it's going to utilize the CPU of my PC. There's another script, select action. Basically, it does the classification, the image classification. And then the output from that determines the rewards. If it was a correct classification, it's going to be given a reward of 1. If it's going to be a wrong classification, it's going to get a reward of -1. Then we store those rewards and repeat all the batches again until the model no longer learns any. That's when the loop will end. Then update policy using policy gradient. Of course, the policies have to be updated after every iteration of the training. When you log the rewards per epoch, then at the end of it, we plot the performance. So this is a code snippet for the reinforced agent. You can see some of the key terms we discussed earlier. There's the policy, there's the rewards, there's you can see actions. They're under the decision component or the classification component. Select action. Yeah, then there's an update policy. Of course, the policy has to be updated once the script runs. So the policy gets adjusted as the model learns. Results. Here we're looking at two graphs which shows the progress of the reinforcement learning model, showing average reward over multiple iterations or epochs. So the first figure on the left is when you run it over 10 times. or over 10 iterations of the dataset. You can see the graph has some points where it's learning, some points where it's not learning, but overall it's basically getting negative rewards, meaning it's not learning. The graph on the right, you see we have increased the number of times we run the training on the dataset from 10 to 100. The pattern is the same, decreasing average reward, which usually suggests the agent is not improving its performance over time, because we would expect this to be tending toward positive until we get a 1. That's when we can know that the model is actually learning. It's getting insight from the dataset. So what the implication of this graph is that the model is struggling to learn, and thus it needs some adjustment to improve its performance. We talked earlier about the reinforcement learning optimizers. There are a number of parameters that can be optimized, so it's part of the things I'm going to consider for further research to try and get this model to a state where it can learn from the data set and and continue learning until the predictions are accurate. Thank you so much. Here is a link to some of the papers I reviewed. This is all the papers uploaded on Google Drive, so this is a link. If you follow it, you should be able to see those papers I reviewed. And thank you once again. I am Patrick Anako. Thank you for listening.